Hello everyone. In this video, we're going to take a look at an example where we're going to find the area under the graph of a function by using the upper sums. So my example, find the area under the graph of f of x is equal to 3x from 0 to 10 using the upper sums. So in this case, we are using n subintervals, we're using n rectangles, and we want to let n become unbounded. In other words, we want to find the exact area by using an infinite number of rectangles. So the first thing, why don't we graph our line? So this is just the function 3x. So this is a linear function. This is a line with a slope of 3. So I'm just going to sketch this in. It goes through the origin 0, 0, and it's got a slope of 3. So maybe something like this. And we want to take a look at the interval from 0 all the way up here to 10. So the area we want to find is going to be this triangle underneath this line. So it is a triangle, so we do have a way that we can find the exact area just by using a formula. But I want to go through the process of using calculus to find this area, and then we can always verify with the area of the triangle. So what we're going to do first is we're going to take our interval from 0 to 10, and we're going to split it up into an infinite number of subintervals. So our subintervals are going to be from x0 to x1, from x1 to x2, and we're going to go all the way up. Our last subinterval is going to be x sub n minus 1 and x sub n. In our case here, x sub 0 is at 0, and x sub n is going to be the x value at 10. Now, when we're thinking about finding the area, we're going to find the sum of the areas of a bunch of rectangles, and we need two things. The first is the width of each rectangle. So delta x, or the change in x, this represents the width of every rectangle. And to find that, we're going to take the entire width of our interval, so from 10 to 0. So if I find that difference, that gives me the entire width. And we're going to divide that into the number of subintervals we have. So every rectangle is going to have a width of 10 over n. The second thing we need is the height of each rectangle. And to start, we're going to think about where the x value is for each of those heights. Now, we are going to be using the upper sums, which means that we want to use the absolute maximum value within each subinterval. If I take a look at this line, that line is increasing everywhere within this interval. So that means within each subinterval, the absolute maximum is going to occur at the rightmost point within that interval. So within this first interval, it's going to occur at x sub 1. Within the second one, it's going to occur at x sub 2, and so on. So if I just draw in a couple of these so we can think about it, we have x1, x2, x3. In between each of these x values, the width, this has a width of 10 over n. So 10 over n, this one's 10 over n. In between x2 and x3 is also 10 over n. So if I want to figure out where each of these x values are, I can take each I and multiply it by 10 over n. So in this first interval is when I is equal to 1. Now I want the rightmost point, so I want x sub 1. So this has a width of 10 over n. So 1 times 10 over n gives me that x value. For the second interval, this is when I is equal to 2. I want the rightmost point, which is at x sub 2. That length from the origin is 10 over n, and then another 10 over n. So that's when I is equal to 2. So 2 times 10 over n, that gives me that x value. And we could keep going. So this is going to generate all those x values for me. And then if I plug that in, f of each of those x values, 3 times I times 10 over n, This will give me the points that are on my line at each of these x values, which will give me the height of all of these rectangles. So we have the width of each rectangle, we have the height of each rectangle, and now we can calculate our sum. So we'll use sum, and we're using n rectangles, and then we'll use our sigma notation. We're starting at I is equal to 1, we're going all the way up to n. F of c sub I, this indicates the height of each rectangle, and then delta x, that indicates the width of each rectangle. And then plugging in what we know, so I got my sigma, I is equal to 1 to n. F of c sub I, we figured that out, is 3i times 10 over n. And delta x, the change in x, the width of each rectangle, is also 10 over n. Now we just want to calculate this sum. So to do that, we're going to use some of our summation properties. The first one is any constants, we can bring those out front. 10 over n is a constant. This 10 over n is also a constant. And we also have the constant of 3. So why don't we multiply all of those together and bring that out front of our summation. So 3 times 10 is 300 over n squared. So that will be out front. And now we have our summation. And then all that's left inside is going to be I. And that works out pretty nice because the summation from 1 to n of I, that does work out. We have a shortcut for that. That ends up just being n times n plus 1 over 2. And now we can simplify this. So the first thing, 300 over 2, that simplifies to 150. That's over n squared. And then I'll distribute n, so that's n squared plus n. Now if we distribute 150 over n squared to both of these parts, here the n squareds will cancel out, so we have 150. And then distributing that to the second part, one of those n's will simplify, so we have 150 over n. And so what we end up with, 150 plus 150 over n, this expression represents the sum of all of those rectangles. And right now we can let n be anything. If we let n be 2, that would represent an approximation for the area using 2 rectangles or 2 subintervals. If we let n be 300, that would be 300 rectangles. But what we want to do is we want to find out what happens when n becomes unbounded. In other words, what happens if we use an infinite number of rectangles? So we want to find the limit as n approaches infinity of our sum, which is going to be the limit as n approaches infinity of this expression, 150 plus 150 over n. And if we evaluate this, so if I plug in infinity, this is 150 over a very large number, so this term will approach 0. So that means that the area under the curve is 150 square units. And why don't we just go back up and we'll take a look at that triangle to see if we are correct. So all the way here at 10, if I go up to the point on my line, so 3 times 10, this is f of 10 is equal to 30. So the height of this triangle is 30, and it has a width of 10. So the area of that triangle, 1/2 base times height, 1/2 10 times 30, so the area is 150. So obviously this is much easier, much simpler, but as we discussed previously, we're trying to come up with a method that we can find the area under any function. So this one happens to be a line, so there is a formula, but not all functions are linear like this. But going through this process and using an infinite number of rectangles, and then finding the limits, we are able to calculate the exact area underneath that curve.